So the first problem that we'll be doing is called Monty Hall problem. I want you guys to interact with me within this, because this is where the probability modeling will come in, where you will see how the probability theory is being used to model the things. The first problem I was telling you is called as Monty Hall problem. The problem statement goes like this. So it was a game. There was a TV show hosted by, his name was, I think, Monty Hall. So it had three doors. There are three rooms which had three doors. So in one of the room there was prize. So behind one of the doors there were prize, and the other two are empty, are having very less price. And there was a contestant. So contestant was asked to pick up a door at random, or maybe howsoever he wanted to pick a door. That was what contestant was told. And after that, if contestant chose the door, so obviously there will be one or two doors left where there is no prize. Let's suppose contestant chose this door. Now there are two doors left, this and this. Out of these two doors, so what this Monty Hall, what the owner of the game will do, host of the game show will do, he'll open one of the doors, which is empty. Let's suppose he opens this door, and he asks the contestants, do you want to switch? Do you want to switch your choice? Because you chose this choice, do you want to switch now? Okay, that's the problem. So is the problem statement clear? Amir, it is clear, and for Asrar, Zakir, is it clear?
Yes, sir. Yes.
Yes, sir.
So the question is now, what should he? If you are a contestant, what will you do? Will you switch the door, or will you be with your own choice? Or if you are with the own choice, what is the rationale behind that? If you switch the door, what is the rationale behind that? That's the question. The question I'll write here is, that's the question is, will you switch? Will you change the door? Basically, will you switch your choice? What will you do? Let's start with Asrar. It's Asrar. What will you do?
Here, I would say that I will be having 33% of chances of getting the prize.
Okay.
Now the probability has increased it to 50% because we have only two doors left, and out
No,
of
no,
these two
but you made the choice. Now, let's suppose you made the choice of this. Like for you chose this door, and now this was opened by the host show, and now you are
by
left
the
with
host.
these two doors. So what will you do?
So the door he opened, the prize was not there.
The price, it's obviously price is not there. Anyways, he opens one of the doors while price is not there. Every time he does it.
I will choose the door which I have chosen earlier only.
So you will not switch. Like in the long run,
Yes,
will you switch or will you not switch?
I will not switch. I will not switch.
You will not switch. What's the rationale behind that? You will not switch. What is the rationale? Why do you think so? You should not switch.
I feel like will, in this case, I will go with my gut feeling only.
Okay, so you will not like, because initially whatever door you choose. Let's suppose you chose this door. For example, in the second scenario, you chose this door. Let's suppose this is your choice. And
Yes,
after
sir.
that, because now he is left with two door, host is left with two door. Obviously, he'll open this door. Okay, now you are left with these two things. Okay, now your strategy
Yes,
in the long run would be to not to stick with my choice. Okay,
to
because
stick with my choice.
you are not going to switch the door. Okay, so Zakir, what will you do?
Sir, among the two doors, the probability is same. That is, the probability is 0.5, 0.5.
So it doesn't
And
matter whether we'll switch or not, huh?
yes, sir, it doesn't matter.
Okay,
Whether,
nice. So Asrar, come up with the guns. Tell them the thing.
Yes, sir, Amir.
Sorry, Amir, come up with the solution now.
Yes, sir. Here we need to switch the doors actually. If we draw the sequential tree,
Okay,
yes, sir. We see, for example, we choose the uh, first one,
okay,
and the host shows the third one is empty.
okay.
So if I switch though, I will get a prize. Same will be if I choose first one and host will uh, open the first one. So
Mm-hmm.
here the probability will be 66
66%.
percent. Yes,
What
sir.
he's because we discussed this problem. Let me put it and let me clarify also, so that you also get the intuition. So the best strategy here is you should switch. So now let's see how to model it probabilistically. Okay. First, how to see the problem probabilistically. So if you see the problem in the first case, if you see Asrar said the right thing. So what will we do? Each of these, if we select at random, so we have 1/3 chance of winning. So that's the probability. So we have 33.33%, like probability will win. That is 1 by 3. Because we have 3 doors, let's say these are door A, B, and C. These are 3 doors. Okay. So these are our doors. This is our A, this is our door B, door C. Okay, what I'm saying you is now, so this is the initial probability. This is initial probability. Now when you choose a door and then host does something. Okay, you will choose something and host will do something. So this is our one door. So I'll make the pictures also so that it's clear for you. Let's suppose some door has a price. That's why this is price. Here the door has the price. Initially everything has probability 1 by 3, 1 by 3, 1 by 3. Okay. Now if you choose a door, you chose, let's suppose, a door which there is now two possibilities. Okay, there are only two possibilities. When you choose a door, so what will happen? Either you will choose a door which contains the price, or you will choose a door which does not contain the price. No price is there. There are these two choices, because out of the three doors you will choose, either it will have the price or it will not have the price. And now what will the host do? Host will open the door which does not have the price. Okay, what will host do? So host every time opens the door which does not contain the price. This is what host does. And now because of this thing, host gives you additional information. Okay, so if you chose the door which has price, and if you switched, in this case, let's suppose you switched, okay, so you'll obviously lose. Okay, but if you switched, if you chose in the initial, say if you chose the no price door, so you'll win. How many of you understood this point? Because there's the whole crux.
Yes, sir, got it.
So what I'm saying is, you chose, there are two possibilities. You will choose a door where you will have the price, or you will choose the door which you, in which you don't have the price. So let's suppose in the first case you chose a door in which there was no price. So you chose this door, let's say. Now this host is forced to open this door because he cannot open the priced door. So he'll open this door. Open this. Now you are left with your choice door and the actual price door. So in this choice where you chose the wrong door, where you chose the door in which there was no price, it's better to switch there because you will win. In the other case where you chose the door, let's suppose you chose this door, okay, and you chose this door. Now you chose the door which was right. There was price. Now host has host, because knows where the price is. He'll open one of these doors. Let's suppose you open this door. If you open this door, so if you switch, what will you do? You'll switch between this and this. So if you switch between this and this, so you obviously go here. Now you'll lose. So why do you lose? So if you choose, so choice, our choice will be, this is our choice. Let's suppose choice. We'll pick up a door with price, with some price, and without some price, without price. Okay, and if we switch with price, we will lose. Okay, if we switch without the price, we'll win. This you should first agree on. Do you agree on this? Asrar, Zakir, Amir, do you agree on this point with me?
Yes, sir.
Yes, sir, it's clear.
Are you clear with this? Because this is the whole crux of the game.
Yes, sir. Yes, sir.
Okay, nice. Now what we'll see is, we'll see in the long run what will happen. In the long run what will happen is, so how many times do you choose the door with price? 1 by 3 probability times. Because that's what I told. I said ki we have one ABC, these are 3 doors, and each choosing each door is 1 by 3. Okay, so there are 2 doors which doesn't have the price, and there is 1 door which has the price. So probability that you will choose the door with the price is 1 by 3. What's the probability you will choose the door without the price?
It's a 2
2 by 3.
It is 2 by 3.
2 by
So
3.
you will choose this with 1 by 3. You will choose this with 2 by 3. Now if you switch, the losing chance you have 1 by 3, and if you switch, the winning chance becomes 2 by 3. Now this is the intuitive explanation I gave you. Like, how many of you understood this? Because now in the long run we'll choose more of these doors, more of these empty doors where there is no price. We'll choose them 2 by 3 chance, 2 by 3 times. Out of 3 we'll choose them 2 times. Like, we'll choose them 66.6% of times. So if you choose this, it is better to switch there because you win when you switch in this case. So that's the reason you will have winning probability of 2 by 3 if you switch every time. How many of you understood this? Asrar, you understood it?
Yes, sir, got it. So the point is, in the long run, if we choose the other door, the next door, we have the probability of winning.
Yeah, if we switch the door, yeah, if we switch the door, but not
Mhm.
just choosing the other door, if we switch whatever the choice you made earlier, you are switching your choice. Now you are saying, no, no, I want to go with the other door. Because he's
Yes,
giving you
exactly.
choice, do you want to switch your choice? Because now we analyzed the probability. You saw this, we made, okay, with the switch, I lose if I chose the right door. If I switch, if I, in the initial go, if I chose the wrong door, so I'll win by switching. Now you know that you will, two third times you will choose the wrong door, obviously, because 1/3 is the probability of choosing a door. So because there are two doors which are wrong, so obviously you will take, you will have 2/3 probability of picking a wrong door. So it is better to switch there. When you switch, because you will win 2/3 times.
But sir, it will be an average probability, because in the second scenario, if we have chosen the door that contains the prize,
Yes,
then
yes.
if we switch in that case, then it will be obviously our false prediction.
Yes, yes, that's what I'm saying. Because in the long run,
In the
by long
long
run,
run,
I
yes, sir,
mean,
it
let's
will be
suppose you play
beneficial.
this game 100 times.
100%.
The code that I sent, the code that I showed, I wrote a code which I sent in the group. So there I have simulated this game 1,000 times. 1,000 times I played the game. I think Asra, Amir, you guys have that code now. Zakir also. So
Sir.
you are in the group, you have that code snippet. So I wrote this code. So what I did is I simulated the whole process with the code. And I was randomly picking up the choice and randomly doing this, having the price in one of the doors. And then what I was doing is, player was in one scenario switching, and in another scenario it was not switching. And you see clearly the probability there was, he was winning 66% times. Please look at that code and you will see the simulation. But you are right, we are not if you, let's suppose, play this game 2 times, so 2 times doesn't give you guarantee that you will win the prize. But in the long run, let's suppose, in the, that's where comes the frequent test approach. What frequent test approach assumes? Frequent
Yes, sir,
test
yes, sir,
approach
exactly.
assumes that it is it goes till, let's suppose, n is equal, it tends to very high number.
Infinity. Mm.
We may not say infinity, because infinity is not a number though, but I have actually taught
No,
this
sir,
concept
actually, I
again,
mean
so
to
it's a
say
high number.
in the long run. Yes, sir.
Yes, yes, in the long run. You understood the problem, Amir, now?
Yes.
Okay. Now we had the next problem. So what was the second problem we gave? I gave the problem of birthday. So that was birthday paradox, it's called. So it's called as birthday paradox. So what is this birthday paradox all about? So birthday paradox says that if you have a bunch of people in the room, if you have a bunch of people in the room and you want to you want to see how many people are needed so that the probability of two people in the room having similar birthday exceeds 50%. The problem goes like this: if you have room, let's suppose I know that with 365 people, I have sure shot probability that the probability is 1, because if we have now 366 people in the room, so by pigeonhole principle, because there are only 365 days in the whole year, so two people will guaranteedly share the birthday. Do you agree on this point with me? If we have a in a room, we have
Sir.
366 people. So if I tell what is the probability that two people will share birthday here, so I can say by sure it's 1, because there are only 365 dates possible within a year. Now I have 366 folks in the room. So
But
it
sir, if someone will have a birthday on a leap year, 29th of Feb, then
no, we're considering there is no leap year though. That's the assumption. No leap year is
then
there. We're considering that assumption.
yeah, then by pigeonhole principle we can say yes,
Yeah,
yes,
you
yes.
can say that with 366 people, we can have short guarantee that two people will share the birthday. So now the question is, how many people do you need so that two people share the birthday and the probability of that is 50 is greater than 50%. So what is the answer intuitively? What do you say, Zakir? What does your intuition say about this? How many people do you require so that the probability of two people having the same birthday exceeds 50%?
Sir, double 365 times 2 times.
Now again,
Please,
think about this. Think about the problem. Did you understand the
sir, can
problem
you
though?
repeat? No,
Sir,
sir,
can
can
you
you
please repeat
repeat,
the problem?
repeat the problem?
The problem is like this. The problem is because now you have a room. Let's suppose you have a room. So within a room, I have some people. Okay. So what I want to see a pair of people. At least there should be one pair of people which share the birthday. So I am asking the question: how many number of people do I require so that two people among them at least share the birthday with the probability of 50%? So probability that people share the birthday among them should exceed 50%. So as you say that probability of people sharing the birthday, if there are 366 people in the room, it's 1, because for sure they'll share the birthday. But here what I'm saying is, I'm saying I don't want with one probability now. I'm saying that people should share the birthday with probability greater than 50%. So how many people do I require in the room? So how many people should be there so that the probability that some two of these folks share the birthday exceed the probability 50%? Did you now understand the question, Asrar?
Yes, sir.
Yes, sir. Problem is clear now.
So what do you think? So how many people do we require?
Sir, 365 plus 150 plus half of 365, because according to pigeonhole principle,
Mm-hmm.
if we have
Do not go into the
365
maths. I'm
whole,
saying intuition. What is, even you're like, if you go mathematically, this is a terrible idea. What you are saying, because you are saying you need more than 365 people.
yes, sir.
Say half of 365.
So half of it. The intuitive, like, it seems okay.
Intuitively, yes, sir.
But what Zakir was saying is we need more than 365. That gives a sure shot probability of 1. But I only want the probability should be somewhat greater than 50, 51, 52%, something like that. Zakir, did you understand the question in a right manner?
Yes, sir. Yes, sir. I understand.
So did you feel that that was a wrong approach? You said the 35 plus something.
Yes, sir. Yes, sir. That will exceed the probability one.
That will exceed the, not even exceed the probability one. It is surely giving me one probability. It is saying that with one probability you'll get it. Amir, what is the answer?
You have told already 23.
It is 23. And can you tell me why?
Sir, if we see, मतलब कि sir इधर combinations बनते हैं.
Okay.
Yes, sir. So if we add up them some, sir, फिर mathematically कर दे थोड़ा बहुत तो इसका 23 आ जाता है.
Let me again give the intuition. So how to think about it. That is the whole point of this course. How to think probabilistically in your brain. Okay. So it is difficult to find what is the probability two people share the birthday. So we'll flip the thing. So because if you know actually some probability, so I said probability of sample space is how much? It's 1. The probability of whole sample space is 1. I hope that you have watched the lecture. You know what sample space. Sample space means all possible outcomes. So in terms of coin flip, so there is heads and tails. So if you tell me what is the probability of sample, it's 1. So if I have an event, probability of an event, okay, is something. Let's call it P of E. And we have something called as complement of event, E complement. So complement means what is not there. So if I have, even I showed in the Venn diagram, I'll just revise it a bit so that you understand it clearly. So I hope that you know, but to be on the same page, I'll just show it again. So this is our sample space. Let's suppose whole of this is our sample space. Whole of this rectangle is a sample space. Let's suppose this is our event E. This is our event. Whole of this which is outside this event is called complement of event. This is E complement. Okay. So complement means what is not there. So this is our sample space. We'll denote it by this omega. So here this is our event E. This portion is our event E. Whatever is outside this E is called, whatever is outside this E is called as E complement. Complement by definition means that. So it should not be present within the E. So I said if probability of whole sample space is 1, because that is how we construct the sample space. So we construct samples in such a way so that an event, if it occurs, it must be present in the sample space. That's the definition of sample space. Sample space is a collection of all possible outcomes in an experiment, in a random experiment. So obviously by definition, its probability should be 1. That's also the axiom of probability. What I'm saying is, now if there is probability of E, so probability of event E, happening of event E is, we denote it with this. Okay, then we have other probability of E complement. Now you know that E union E complement, this gives omega. Amir, do you agree with this?
Sir.
So this gives the whole sample space. Any event, if you take it and if you take the complement of that event, it will give the whole sample space. In terms of head and tail, if you toss a coin, we have head comma tail. So let's suppose if I have probability of head. So what is the complement of probability of head? It is tail. It is probability of tail. That actually, if you just add both of these together, so you will get the whole sample space. So probability of head, you will get head. What is the head complement? It is tail. Similarly, if you toss two coins, so tossing of two coins means you will have head head possibilities will be head tail, tail head, or tail tail. These are 4 possibilities. This is all the sample space that we have, because other than this nothing can happen in the coin. If you toss 2 coins, or if you toss coin one after the other, you make 2 tosses, so it will be both toss will be head, or one toss will be head, other toss will be tail, or one toss will be first head, first tail, then head, then or both toss will be head. This is our sample space. So if I am asking you, let's say event E is 2 heads. 2 heads is the event. So what is the chances of 2 heads? So if I say what is E complement? E complement basically means either one head or no head. Okay, so that is E complement. So if I say E is 2 heads, E complement should be 1 or 0 heads. That is the complement. That's E complement. So if probability of E, let's suppose here is, now if you see now the point is this that I wanted to prove. E plus E complement should be omega. If you know 2 heads, that is this choice. Okay, and 1 or 0 heads, that is this or this choice, because this is 0 heads, this is 1 head, 1 head. So now do you understand that E union E complement is the whole sample space? Do you agree on this point with me?
Yes, sir.
If you agree on
Yes,
this
sir.
point, so can I write that probability of E union E complement is probability of whole sample space? Can I write this?
Yes, sir.
If I can write this, now you know that they're disjoint events. So if they are disjoint events, now can I write by the second axiom of probability, P of E plus P of E complement is equal to, this is 1. Can I write this?
Yes, sir. Yes, sir. Obviously.
If I can write this, so can I write P of E complement is equal to 1 minus P of E?
Yes, sir.
Yeah, so this is obvious, but I just wanted to prove it by using the axioms of probability. Okay, so this is one the property. So we're discussing the birthday paradox. So I said it is a bit difficult to compute the probability of two people having the same birthday. So what is easy then? The easy part is complement. What is the possibility that two people do not have the same birthday? It is easy to compute. Okay, let's suppose I have 2 people. These are my 2 people. I want to compute what is the probability that these 2 people do not share the same birthday. It is easy to compute. Why? Because there are only 365 days. There are 365 days, and it's not a leap year, so there are 365 days. So if this guy shares a birthday, let's suppose he has some date birthday. So now if these 2 folks do not want to share the same birthday, so now his birthday should be out of the 364 days. Whatever this guy chose, it should not be his birthday. Do you agree with this?
Sir.
Yes, sir.
Yes, sir.
So what I'm saying is, I'm saying if this guy has some birth date, so that is the date he was born on. So I'm trying to compute what is the probability that they don't share the birthday. So out of this 365 days, he should not choose only that one day. Okay, he should not choose that one day. That's what I'm saying for this. So I can just directly write, for example, now he has 364 possibilities. So he has 364 possibilities to choose from, and out of 365, that's the probability that 2 people will not share the birthday. Is it clear?
Yes, sir.
Can I say the probability of like 2 people not sharing birthday is equal to this?
Yes, sir.
Okay, so if you agree on this, so what I'm saying is, now I'm saying I know that probability, this is my event. Now I had probability of 2 people sharing birthday. Okay, this is sharing. Let's suppose probability of S means sharing birthday. So now I know that probability of sharing birthday is equal to 1 minus probability of not sharing birthday. Because for me this is easy to compute. This is a little bit hard, because combinatorically this problem is hard to compute if I because I cannot intuitively come up with an answer for this. So what I'm doing is, now, so I'll compute this. I'll say, let's suppose now I have n people. If I have n people now, so these are the people I have. Let's suppose n people. For the first people, if there is only one person, so what is the probability that he does not share the birthday with himself? What's the probability? Guaranteed 1, because he won't share. So because there is no chance of sharing the birthday, because there is no other person to compare. So we can write, this is the probability of the first person is 365 by 365, because he has 365 choices and he can choose any birthday. And then, as you know, these events are independent because they don't affect each other. So what will happen for the second person? So for this person, how many choices are there now? Now one choice is gone, because this guy took the one choice. So he's left with only 364 choices out of 365. Okay. And then what is the probability for this third person? Now he is left only with 363 choices, because two choices are gone. The first guy took, the second guy took. Now he's left with 363. Now what I want to do is, I want to say how many people like this, how many of these factors will I take, so that 1 minus this factor, let's call it f factor. Okay, 1 minus this factor. So probability of birthday sharing, it should be greater than 50%. So probability of not sharing, and this factor basically should reduce, and this factor should somehow, it should be some 50% greater than this 50%. Okay, now if you compute these sort of numbers, so you will see you only need to multiply such numbers 23 times. You only need to multiply it 23 times, and you will get the answer like this: 1 minus 365 factorial divided by 365 raised to power 23, 342 factorial, something like this. And this will give you around 0.507. Okay, that's greater than 50%. How many of you are you clear with the birthday paradox now? Did you saw how do we solve this problem?
Yes, sir.
So how did we solve the problem? We said, if there is some event which is hard to calculate, let's think about the complement of the event. Is it easy to compute the complement? That's what we did. And first we tried to prove the complement property, and this was given as a homework to prove those proportions. So we had these three axioms, and again to write those three axioms. So the first axiom was, what was that, Amir? What is the first axiom of probability?
First axiom was sir,
Probability of an event should be
uh,
between 0 and 1.
between 0 and 1, yes, sir.
So it should, 0
Second,
means it will not happen, 1 means surely it will happen. So in between, this is the first axiom. What is the second axiom? Second axiom was that probability of the sample space, whole sample space, is equal to 1. Okay, what is the third? Third was if there are disjoint event. Disjoint means if they have nothing in common. So disjoint, I showed you, if there are events like this, they have nothing in common. So probability of union of events which are disjoint. So this is equal to probability of summation of these. This is equal to summation of, let's suppose, I to n, and this is I to n. So that's what I did here. So probability of head union tail is equal to probability of head plus probability of tail. Why? Because they are disjoint. They are not dependent on each other. So we'll see what are these disjoint, what is, if there is intersection, we'll see all these cases. But here, if you see this, so from this three axioms, we could derive one of the properties. I said the probability of an event complement is equal to 1 minus probability of that event. That is one of the axiom that we computed from that. Okay, and there are a lot more that I gave you which you can compute, but because of this, we could solve this birthday paradox. The birthday paradox was how many people do we require so that the probability of two people sharing the birthday exceeds 50%. Now we saw it is 23, so that we only require 23 people in the room so that their birthday, the person chances of their birthday being sharing a birthday is greater than 50%, and that is nearly 507 or something that we got. Okay, 0.507 with 23 people. Okay, now I'll tell you to model the problem. Now you guys help me with the modeling of the problems. Now I showed you some paradox, I showed you where to probability use, because probability gives you a notion how to think of uncertainty. If you are in an uncertain situation and you want to analyze the thing, if you are trained in probability, that time you can analyze situation better than the other people. Okay, so let me tell you a story about me, what happened. So I have some traders who are doing some forex marketing. So these folks told me, can you help us building a random trading bot? Not it should not be random, it should take trades based on some patterns and things. So how many of you understand this trading, stock market, forex trading? How many of you at least have heard of these? How many of you have heard of this? Zakir, Asrar? Nice. So what they do is, so they put there some money and they expect that currency will have some fluctuation, so they'll sell or buy something, and it'll their speculation will be right and they'll earn something. So they told me, okay, can we create a bot which will take automatically trades and it should win? Okay, and these folks were from the economics background and they know a lot of economy and stuff, but they were not trained in probability. So what I made a claim to them, this that looked a random to me because they had some patterns like this, something like this. So they were saying this is support, this is resistance, and this is stuff like that. So I said to them, okay, let's model the whole thing with probability. We'll see if the probability favors your thing. Okay, if the probability favors whatever you are doing, you are taking trade at this point, you are taking trade at this point. If it favors, then probably we should take. If probability says your winning chances are greater than, let's say, 50, then you should take a trade. Or if it's 70, you should take a trade. Otherwise, you should not. So these folks were all doing some analysis, and they were saying I should take the trade. Let's suppose whoever, because I speculate the market will go down, but based on what intuition they had. Okay, and I'll tell you one of the stories from them, and most of these people are making losses. So when I came up with the probability, I told them, let's model this whole with the probability. We'll see what are the chances of you guys winning over there. Okay. So when we modeled that, it nearly came to be a random walk. It was a nearly random process for these folks. So I said them, even without taking analysis, you are hitting the wrong tool, because probability says that whatever trade, the problem that you are doing is that you are believing on your intuition, and that is the reason you are, why are you in the losses. So if you want to make profit, so your probability should get greater than this. So I modeled the whole process with this probability. So what happened? So because of that bot, if it was given enough knowledge, and if it was given enough data about the thing, it could make really good trades. And trader was like sort of surprised, how can it make so much good? Because I modeled the whole problem with the probability, and by having the data, then training the model and trying to fit it with the data, and we were able to get this. But we were able to establish two more things: that this market in the long run is random. Maybe in the short term it shows some cyclicity property, it shows something, and but if you see in the long run, by using probability, this market will look random to you. Okay, but if you have good data, if you have data about weather forecast, interest rates, unemployment, and all of these things, you can predict the market also. Okay, that's the reason why you should read probability theory, because it gives you tool to analyze uncertainties. There was a guy named Simon. So he was a mathematician. Okay, he was a mathematician, and he was interested in abstract pure maths. So what happened? He suddenly got interested in finance. After a time, he got interested in finance. I think he was from MIT. So what he did, he opened a hedge fund. So each year he was earning 66% returns by using these complex machine learning models and using the probability theory Markov chains to model this. And that means if you have invested $100 when you opened the hedge fund, you will be easily earning around some $1.5 million from this, because the effect is compounding. That's why you should know it, because you can model the real world problems by using probability. Even that's what I said in the first lecture. Machine learning inherently is probabilistic in nature, because we want to model the world, and world is uncertain around us. So we have this probability theory gives us models to analyze. Now we'll see how to model a problem. If there is a problem, how should I model it probabilistically? Because you have been hearing about the problems. Okay, I'll toss a coin, then you are saying head tail is a possibility, this is the outcome. What if you are faced with a real world problem and you are said, okay, can you model this problem? That time you should be able to know how to create a sample space and things like that. And now let's go to the first problem, and I'll tell you what problem is, then I will try to model it combinedly, and then we'll see how to analyze the situation. Okay. So question Asrar asked is, which approach is better, Bayesian or frequent test? So I won't say one is better than other. So what happens in frequent test approach? You say that let's suppose a basic axiom you will take: probability of any event is equal to number of favorable things in that event divided by number of total things that are in the sample space. So this is what they. But here you assume that all the things that are in the sample space. So they basically, if you use this frequent test approach formula, so you say that they have equal probability. So let's say in terms of we have sample space for coin, we have head comma tail. So we assume that this is 50%, this is 50%. This is your sort of prior belief about these things, and you say, okay, now we can model it and we can perform experiment a lot number of times. But the problem with this approach is sometimes you cannot perform the experiment, let's suppose 10, 100, 200 times. That time you can perform experiment only 1-2 times. That time and you have the belief, and let's suppose I'll tell you one problem. I'll see how will you model it. What is the probability that there is life on Mars? What is the probability? So one model can be there is or there is not. So how much probability is there? Asrar, Amir, what do you say? Okay, I will answer from each of you.
The later one, there is not the.
So what is the probability? Can you give me a number? So there can
Same.
be, there can be not. So how many?
0.5.
0.5, huh?
Yes, sir.
So how many of you agree that 0.5 is the probability of life on Mars? There is a probability that there is life on Mars. The probability is 0.5. How many of you agree with this?
Sir,
Doesn't it feel wrong?
yes, sir, it feels wrong, but
Doesn't it feel
according to
wrong?
physics, yes, sir.
It feels wrong by the intuition also. Why does it feel wrong? Because we modeled it in the wrong way. We said there is only two, but there is not. But we have prior belief also. So what is our prior belief? Our prior belief is that prior belief is because there is no atmosphere, there is not this, it is way let's suppose near to the sun, or there is different soil and things like that. And that boils down that we believe that only 0.1% chance is there that we have probability. The probability of life on Mars is 0.1 according to our prior belief, according to our intuition. Once we see some evidence, we'll update our probability. We'll not model the probability like this. There is or there is not life, then there is one by two chance, 1/2 chance. Asra, do you get it?
Yes, sir. Yes, sir.
That's why frequent test approach, sometimes you have some prior belief, and with the evidence you update your belief. You say I had this belief, but I got some evidence, and I am now updating the belief. I'm saying now probability has increased or decreased. So prior belief was because I see no atmosphere, because we know all of these things. I'll tell you, what is the probability that tomorrow the sun will rise? It will or it will not? Is it 50-50? What do you say?
One.
It is one. It is nearly
Because
one.
it
Why?
will
Because the prior belief you have. You have some belief. And frequent test approach will also tell you the same thing. So frequent approach will tell you, because out of the past 1,000 days, so how many days had the sun risen? So you'll say in 1,000 it rose on all the days, so it is one. But Bayesian probability tells you you have some prior belief, and based on that you get some evidence. Now if you get an evidence, you don't change your belief. What you do, you update your belief. Like, I'm impressed by, like, really cool. This is a really cool idea by Bayes, and even he was sort of fearful to publish it. You know this. He has not published it, but some of his friend, when he died, so he went to his room and to see in his closet what is there, and he found this. He said, "What is this weird thing he has written?" And then they formulated this Bayes theorem. They said, yes, it really makes sense in the real world. That's why we have separate courses on Bayesian probability, Bayesian belief networks in the machine learning and stuff. I hope that I cleared some of your doubts, that it is the world is not black and white. It has gray areas also. Now, the topic I'll take is how to model the things probabilistically. If there is a thing, if there is a real world phenomenon happening around you, the first thing is to model the problem. That is the really important thing. And this is where I see these school folks which are teaching probability, they don't focus on this. So they're teaching probability, okay, we are flipping the coin, we are doing this, we are doing that. But the whole intuition of probability is that it should teach you how to think probabilistically about uncertainty in the life. So if there is some uncertainty, what decision should I go with, because I have some your brain should be trained like that. Let's say we have a problem. The problem, I have three coins. I have three coins. So one coin, I have two 5 rupees coin. So I have two coins which are 5 rupees. Two 5 rupee coins I have. So one coin is 5 rupee, other coin is also 5 rupees. So these are two coins I have. Okay. And then other coin I have a 10 rupee coin. I have another coin which is of 10 rupees. One coin of 10 rupees. Okay, so we are playing a game. Let's suppose you are gambling and you are going to play a game. So they take some 10 cents or maybe 10 rupees for entering the game. So they take 10 rupees to enter into the game. Okay, this is the number of rupees they take. So what happens is, they'll tell you to toss the coin. They'll tell you to toss this coin. Now these coins will have heads and tails. So whichever coin falls on the head, you win that amount. So when do you win? So you will flip first 5 rupees coin, second 5 rupees coin, then you will flip the 10 rupees coin. So whatever the coin landed on head, you will win that much amount. So the first problem now is, what is the sample space of this? Okay, so I'll ask you the question. The question that I'll ask you: what is the probability of winning? What is the probability of winning? Please think in this framework first. Now, first thing is, we have to create a sample space, and based on that, we can assign probabilities to the events of sample space. Then afterwards, we'll see which event in a sample space gives us the winning chance, and in which event do we win, and after that you can compute this thing. Again written in the problem is we have 3 coins. So among these 3 coins, so 2 coin of 5 rupees, so we have 1 coin 5 rupees, second coin 5 rupees, then we have one more coin which is of 10 rupees. Okay, then we are playing a game. This is our game that we are playing. So we are, for entry fees is 10 rupees for it. So you are giving 10 rupees to enter in the game. So the game is, now you are flipping the coin. You are flipping your 5 rupees coin. You are again flipping your next 5 rupees coin. You are flipping your 10 rupees coin. Among those 3 coins, whatever coin lands at head, okay, you will win that much amount. If let's suppose this coin lands at head, you will win 5 rupees. If this coin lands at head, you will win 10 rupees. So my question is, what's the probability that you will win something, you will not come losing things? Okay, so the first thing is, we'll have to come up with a set of possible outcomes, or what will be the outcome. So we can model it differently. The first model that I'll say is, how much amount can we win? That's the first sample space. We can win 0 amount. How can we win 0 amount? Because we have, this is the possibility, we have 5 rupees, 5 rupees and 10 rupees. So 0 amount means, so we entered by giving plus 10, so we gave 10 rupees, so actually our whole debt is minus 10 right now. So either these two coins flipped on the head and this flipped on the tail, so you won these two, but you also gave entry fees of 10, so it nullified, you won 0. Or maybe these two were tails and this was head, you won 10 rupees, but you already paid the fees 10 rupees, that gives you 0. So do you agree that there is a possibility that we can win 0, the game can be draw?
Yes,
You
sir.
agree with this? Or we can win 5 rupees. How can you win 5 rupees? So we have this 5 rupees, 5 rupees, 10 rupees, and you have paid 10 rupees. So maybe what? How can you win 5 rupees? Because you won 15, but you have given this 10 as your entry fees. So in total you will win 5 rupees. You can also win 10 rupees. How can you win 10 rupees? So maybe you will win 10 rupees, let's suppose, by winning all of these.
All
If
the three land on head.
they land on the head and you will win it. Can you win
Is there a
50 rupees?
chance that sorry to interrupt, sir. Is there a
Yeah.
chance that we pay 10 rupee first, the entry fee, and the we lose every game?
Yes. You can lose everything. You can have this minus 10 also. That's what I'm saying. You can win. Then you can have minus 5 also. You can have minus 10 also now. That's why these are all possibilities of the amounts that you can. This is our loss or gain, loss or gain. Because initially it can be draw. We can win 0. I showed the possibility. We can win 5 rupees also. We can win 10 rupees. So we can also have minus 5. We can lose the money. How? Because we gave 10 rupees entry fees and we just won the first. We just won the first thing. And out of the other two, they landed on tails, and we just won 5 rupees. But we paid 10 rupees of entry fees, so it gave us minus 5. And how can we how can we lose 10 rupees? Because everything was tails there. So we lost everything. So this is the possible outcome. This is the possible loss or gain. Okay, is it
Yes, sir.
okay?
Okay, sir.
This is when we took our entry fees into account. Entry fees into account. Let's suppose if we do not take entry fees into account, if we just see how much amount are we winning without the entry fees, then what is that? So that will be 0, 5, 10, 15, 20. You can win everything. 20 rupees, you can win maybe these two, you can win 15, you can win 10 rupees, maybe this or this, you can win 5 rupees, you can win 0. Everything. This is when the entry fees is not taken into consideration. Entry fees not accounted. So we are not accounting this entry fees. Or maybe you can do one thing. You can say, oh, I can analyze this game in some other way. I can, because my question is, what is the probability of winning? That's just I want. So now I can say probability. I can either win. I can win the game. I can lose the game, or it can be draw. These are 3 possible chances for me. These two are equivalent, or these two are sort of equivalent. But this is somewhat different. Okay, here we neglect the actual amount which we lose or which we won. We just care about winning, losing, or is it draw. This is again a sample space. Now the thing is, we need to give probability to each of these elements. Okay, so what's the thing now? Now we need to give the probability to this. So we can again create a sample space like this. This is one what I can do is, now I can create it like this. I can say it'll be omega can be like this. Omega can be like one head, and then I have 2 heads or 3 heads. This is my winning. Okay, here I win. In this I win. This is my winning situation. Okay, so even I can enumerate all of these things. The point being is, so if you understood this point, then I can go further because I have to model it. So what I'm saying is, now these are our models. Either you can choose this equivalent. These two are equivalent things. So here now we'll choose the probability to assign these things. Okay, the probability of winning the game. What is the probability? And even if you see this model or this model here, if you assign equal probability to winning, losing, or drawing, okay, so you'll say what is the probability of winning? It is 1 by 3. Even if you choose the equal probability, the point is, if you choose equal probability, 1 by 3, 1 by 3, 1 by 3, what is the probability of winning according to this model? It is 1 by 3, isn't it?
Yes, sir.
But if you see, let's suppose this one, what's the probability of winning? Let's suppose here, what's the probability of winning in this? So these two are the possible chances of winning. Okay, and otherwise you lose this -5 and 10. This is when you take entry fees into account. Okay, so the probability becomes probability of winning is equal to 2 by 5. Don't you see different answers? How
Yes,
many
sir.
of you are able to understand this at least? What I'm saying is, here if I give the equal chance to all of these, so the probability of winning in this case will be 2 by 5. So if you see in the here, the probability of winning will be 1 by 3. But all of these models are perfectly right. Why are we wrong then? Asrar, what do you think? Why are we wrong? Are we wrong even?
All are the three are correct, sir, I guess.
If all are three are correct, do you see at least like I want entry fees here? It is not considered because it shows winnings only. So maybe I can remove it. I'll remove this part. So at least with the two models that I just showed you, so here the probability of winning is 2 by 5 because in these two scenarios I win out of the 5 scenarios. And if you see here, out of these scenarios, one scenario is winning. So here probability of winning is 1 by 3. In this case, probability of winning is 2 by 5. What is right then? Or where do we go wrong?
Is this because the sample size of the sample space in the first case is bigger?
No, but it is not that, because the problem, what I'll tell you, the problem lies here because we assigned each event equal probability. So here we assigned winning equal probability. We assigned losing draw. We saw these are equally likely to happen. But it is not the case. So for that, we should write all the possible outcomes. Okay, and then we can assign probability to each of these and compute the probability. And for that, we'll see what are the possible outcomes for this. So that's what I was trying to write. So how to write that? So we can have something like this. I'll write pi like this. So because we are flipping 10 coins, so if you want to write it easily, so you can write it like this: head head, head head 4, and tail 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 tail. Then you can write head head, tail tail, head head, tail tail, head tail, head tail, head tail, head and tail. Okay, so now this is the whole enumeration. Now these are all possible outcomes. Now what you can do is, you can say, okay, here what do you win? How much do you win? In this case, how much do you win? Now these are equally likely because you enumerate everything. So how much do you win here? Head and head, you win 10
10.
rupees. Don't you win
Yes,
10?
sir.
Because that's the highest you can win, 10. So how much do you win here? The first coin is 5, 5 and 10. This is 5, 5, 10. Okay, first coin, second coin, and this is third coin. So in
Zero
this
in
case,
zero.
no,
Zero.
you in 0, right? So in this case, what do you earn?
5
Five.
rupees.
5 rupees. Nice. In this case,
Mm,
-5. Huh?
will be minus 5, yeah.
Here,
5,
5.
5 rupees.
Here, what will you win?
-5.
Minus 5.
-5 plus 5. Minus 5,
Minus
because it's tail, right? So what will you do here? It is
0.
0.
here
-10.
-10 because you lost everything. Now you see that. Now we can assign. So this 10 appeared how many times? Because each of these are equally likely. So each of them have 1 by 8 probability. So now winning this 10 has 1 by 8 probability. Okay, 0 and 0 it has. So now events possible we had are 0, 5, 10. What else was there? 0, 5, 10, -5 and -10. For sure you said that this is only 1 by 8. Okay, And what's the probability for these zeros? 2 by 8. Do you see it? And what's the probability for 5 plus 5? 5 and 5 here. It's also 2 by 8. What's the probability for minus 5? So minus 5 is over here, minus 5 is over here. So how much is this? 2 by 8 again. So what's the probability of this minus 10? It is 1 by 8. Now we assign the probabilities to this. Okay, and we know that the probability sample space should be 1. This is 2 plus 2 plus 2 plus 1 plus 1 is 8 by 8. This is 1. So now we distribute the probability in the right way. Now what's the probability of winning? So probability is all of these events are disjoint. Okay, so now we can add these probabilities over here. So what is the winning probability? This and this. So winning probability basically is 3 by 8. Is this clear?
In the last case, sir, how do we add up with minus 10 when we have all the three tails?
How do we?
How did the result came up with minus 10? Because we are losing everything here.
Yeah, we are losing everything there because there's a 10 is the entry fees.
Okay, sir.
This is the entry fees that we paid because we did not win anything, so we lost everything. So that is the 10 rupees. Why did you even get 0 over here? Because you paid 10, you won 10. That's 0. So based on these, all the possible enumeration that are possible there. So I assigned the probability to the sample space now. Even now, I can give probability of that lose, win, and this is one sample space. This was our sample space 1. This is our now sample space 2. Let me write that over here. Sample space 2, let's suppose was lose, win, or draw. So what's the probability with lose? So why do you lose? So you lose over this negative, negative and 5, negative and negative. This is 3 by 8. You lose over here, lose over this, lose over here. So where is this win? Where do you win? You win again 3 by 8 times. You draw the game how many times? 2 by 8 times. Okay, by enumerating all the possible things. If you made a sample space, now you also assign them probability. That's why it's called a probability function. So probability function, it takes some input and it assigns it a number between 0 to 1. You might have heard, let's suppose we have a probability function. What probability function does? To an event, it assigns some probability value. That's what we did here. So we saw how to, there are possibility we can create a sample space like this. We can create a sample space like this. Okay, and how to assign the probability to each event now. For that, we enumerated everything. We said what are the possible things that will happen and how do we win or lose. Is it clear? So what's the probability of winning now?
2 by 8.
3 by 8.
8, sorry.
3 by 8. So should you play this game? Because it's better to draw also. So draw plus, if you see draw plus this, it is good probability, I'll say. It is I think 5 by 8. 5 by 8 is quite good probability. Okay, better than, I think better than 1 by 2. Okay, so this is how we model the problems. So you have a problem, you try to construct its sample space, and there can be different ways to construct sample space, and then you assign the probabilities to each of these events, each of the one event. So then after that you can use the axioms of probability, and there will be a lot of questions that we'll do, but this is the introduction that I wanted you guys to at least have about the probability. It is, this probability is not just assigning some heads and tails, we are rolling a die, rolling this actually happens in the real world. Okay, I'll stop the recording here and maybe I can take your question and discussion with you.